So good morning, everyone, and thank you very much to the organizers for inviting me to give this lecture series. So I want to talk about special value conjectures, and I will give 2 talks about Motivic L functions and 2 talks about zeta functions. Historically, the conjectures for Motivic L functions came first, even though they're more complicated. And so today, I'm mainly talking about very concrete things, some formulas you probably have seen before, and how this translates into this somewhat strange formalism of the fundamental line and determinant functors. And so there will be lots of history today. And then in the next talk, I will give the general formulation for arbitrary Motivic L functions. And I will say a little bit about proofs. Proofs are mainly via techniques that I'm not so much an expert in, and that will be covered in other talks of the lecture series. And so then the next 2 talks, 3 and 4, they're about more recent work of myself and Baptiste Morin, where we switch somehow the point of view slightly from Motivic L functions to zeta functions. And so the material on Motivic L functions is maybe 30 years old. So this is very much established now, and people have been accumulating evidence for this conjectural picture by proving special cases. Okay, so what are we talking about? So first, let me say a few words about the distinction between zeta functions and Motivic L functions. So zeta function is actually conceptually much simpler. It's simply a counting function for a system of Diophantine equations in finite fields. So in technical language, we talk about an affine scheme of finite type over spec Z. So it's given just by finitely many equations in finitely many variables. And you want to count the solutions of these equations in finite fields. So because the maximal ideals of such a ring, as written there in scheme language, the closed points, they just correspond to solutions in finite fields of these equations, F1 to Fn. And so one simply writes down this counting function. In the simplest case of spec Z, it's just the Riemann zeta function. And then L functions are actually much more complicated, but the general idea is one takes the variety and decomposes it under correspondences. So one takes only a piece of the cohomology of the variety. And there's another switch in point of view. Instead of talking about arithmetic schemes over spec Z, one talks about smooth projective varieties over the rational numbers. So, so this is just the generic fiber of an arithmetic scheme. And it wouldn't include varieties over finite fields, whereas the first point of view includes varieties over finite fields. And so, so one can kind of decompose such a variety under correspondences, take an eigenspace, for example, under a group action, a group that would act on this variety. But one cannot do it for the variety itself. One has to do it with cohomology theories. You have to linearize, and then you can take a direct summand of the cohomology. And so the idea is a motive is some kind of universal cohomology, and then it has different realizations, which are concrete theories you can construct and attach to such a smooth projective variety. So like the cohomology was usually called the Betti realization of M, which is the usual singular cohomology of the topological space of complex points, algebraic de Rham cohomology, and Analytic cohomology with its Galois action after changing X, base changing to Q bar. And out of this data, one forms an L function, and one forms the spaces and the objects in terms of which the special value is described. So, and I will spend this lecture and the next one actually illustrating how this works. So one example of such a direct semantic composition is you decompose the total motive of x into its hi's, into its ith graded pieces. So this should be conjecturally be given by an action of some algebraic cycles on cohomology, even though it's not known for dimension bigger than 2. Okay, so one takes eigenspaces under correspondences, and then one gets an interesting class of L functions. And this is really a very remarkable class of functions, which appears in at least 3 different guises. So what I'm talking about will be motivic L functions, which come from arithmetic geometry, as I was saying before. But most proofs of these properties that one expects for these motivic L functions, they go via automorphic L functions. So the idea is, in many cases, one can identify a motivic L function with an automorphic L function, which are defined completely differently in terms of representation theory. And there's a third description of the same class of functions, going back to Selberg, which just comes from complex function theory, from analysis, where you say you have a class of complex functions which have an Euler product and a functional equation of a certain type. And this should also describe the same class of functions. So there's a one-to-one correspondence here between the analysis and the representation theory conjecturally. You might have noticed there's no one-to-one correspondence between the automorphic side and the motivic side. There's more automorphic L functions than those coming from arithmetic geometry. The arrow only goes one way. So a very intriguing class of complex functions, very different from other complex functions you might have seen, like in differential equations and so on. And there should be a theory of those functions which lives on the motivic side, which currently one has only over finite fields. And special values are a first step maybe to such a theory. So as a basic example, you can think of Dirichlet L functions. They correspond from the point of view of arithmetic geometry to cyclotomic fields, which in the slide before I was talking about smooth projective variety. So this would just be a field extension of Q. So it's a 0-dimensional variety. And from the automorphic side, it will correspond to automorphic forms on GL1 over Q, the multiplicative group over Q. So the automorphic side basically sees only the piece of the cohomology, and then it organizes the information according to the symmetry group of this piece of the cohomology. So this is just GL1 or Q in that case. You have a one-dimensional object. And from the Selberg class, this would be described as degree 1 functions in this terminology, which I'm not going to go into. I will talk about cyclotomic fields a little bit. Okay, so these are the functions we're interested in. And the formulas for their special values, maybe the first one, I don't know, but I would guess that's the first one. Historically was Leibniz formula, this nice identity, giving a formula for the arctangent series. And then Euler proved a couple of more such formulas, and it's quite intriguing what was going on there. So he could only prove formulas for the sum of the even powers of the inverse integers. And for the odd powers, again, like in Leibniz formula, for example, the third power, you also have a formula, but you have to take the alternating odd powers of odd integers. So I think that was an open problem at the time, but it's not clear a priori that there should be a formula. So if you take an odd exponent, there is no formula in terms of powers of pi. So very intriguing if you learn this in the first calculus course and you wonder what's going on. And also these rational numbers, they have some nice generating function in terms of Bernoulli numbers, but there's no closed form for the rational numbers occurring there. And so from the point of view of this talk, the Riemann zeta function would be a motivic L function, and Dirichlet L function would be an automorphic L function associated to, well, you could call it an automorphic form, but it's just a character of the group of residues mod m, a multiplicative character. And if m is 4, then you exactly get the alternating sum over odd integers, because by definition, this character, if you evaluate it as some integer n, which is not prime to this conductor m, then you get 0. So it's just sifting out the odd integers, and then it's alternating. So that's a character of conductor 4. But to understand these formulas, as nice as they are for Dirichlet functions, one has to generalize to get a better point of view. So the Riemann zeta function generalizes to number fields. Again, a number field has a zeta function, which you can write down either as a sum over the ideals or an Euler product over the prime ideals. And again, you can view it as the zeta function attached to an arithmetic scheme, spec OF, or to a motive, the H0 motive of the generic fiber, spec F. So these 2 points of view that I was mentioning at the beginning of zeta functions and L functions of motives, they just coincide in the 0-dimensional case for number fields. And then what's surprising is that, so these formulas that I was mentioning before, when you generalize to number field, at least at S equal 1, where of course the Euler product doesn't converge and the series doesn't converge, but you can analytically continue, and you always look at the leading coefficient. So, so when I say special value conjectures, I always mean the leading coefficient in the Taylor expansion. So in this case, it would be the residue. And there is this well-known formula, the analytic class number formula, which has all kinds of arithmetic invariants of the zeta function combined in this residue. So one has the class number H, the cardinality of pic OF, the pica group or ideal class group of OF. One has the number of roots of unities or the torsion in the multiplicative group. R is the regulator, which measures a co-volume of the unit group in some very simple real vector space indexed by the infinite places. And R1 and R2 are just a number of real and complex places. So you get all kinds of interesting invariants mixed up in this formula. And of course, it can be used to prove asymptotic properties of number fields. For example, study class, towers of unramified extensions and so on. So it's a very useful formula from arithmetic. But so it gives a hint that these formulas might be related to arithmetic, the formulas I was mentioning at the beginning. Okay, so maybe I can be brief. So it's really nice to plug in what's going on. If you just take the field Q again, there's one real place. All the interesting invariants are trivial for Q. Rank of the units is trivial and so on. And so you just have 2 over 2. The residue evaluates to 1. 1, 2 is coming from the global number of units, and the other 2 is coming from the local number of units at the real place. And if you take a cyclotomic field, Q adjoint Q zeta M, then you have this basic fact, which is sort of one of the first things you prove in an abstract algebra class on Galois theory, that the Galois group of this field is actually the integers mod m multiplicative again. So the same group that appeared from some maybe automorphic point of view now appears from an arithmetic point of view. And that's behind reciprocity law. So that's why I was calling this arrow a reciprocity law, sometimes called Langlands reciprocity. In general, you identify an automorphic group with some symmetry group of the motive, if you like, or the geometric object spec F. And so you can decompose this Dedekind zeta function into a product of Dirichlet functions in that case. So it's an easy exercise with the Euler product. And for example, again, if you take m equals 4, the Gaussian numbers, its zeta function decomposes as zeta s times the Dirichlet of the unique character of conductor 4, and you get Leibniz formula as a special case of the class number formula. Okay. So now, how does this generalize? I mean, it's not at all clear that it should generalize, but people discovered in the early 70s that it does to these other integers, like Euler's formula for the sums of inverse squares and so on. They also have, if you pass to a general number field, an interpretation in terms of arithmetic. So if you look at the class number formula at s equal 1, it involves what's called the K0 of OF. So that's a construction which is sort of an object of, that's hard, I mean, one can probably make a whole lecture series just about K-theory. It's an object of higher algebra. So instead of algebra with numbers, you make algebra with modules. So the K0 is the group completion of the monoid of projective modules over this ring OF. And so S equal 1 involves K0 and K1. And it was discovered in the early 70s. I think Lichtenbaum was the first to kind of conjecture it. And then after Quillen had defined higher K groups, and then Borel proved a lot of things, that the value at M, now of course it's an actual value because the Euler product converges, is related to higher K groups. And yeah, so I just leave K groups as a black box at this point. One could say much more. Maybe I'll try out my my stylus here. I can actually write into these things here. So Ki involves ideas from a rather different area from homotopy theory. So Ki of a ring is actually defined as the homotopy group of a certain space where you take the classifying space of the category of projective modules and isomorphisms. So that's a monoid under addition, but then you group complete, and this group completion produces the higher K groups. I mean, the actual monoid just has a pi 0 and a pi 1. You have isomorphism classes of objects and automorphisms of objects, which is sort of the fundamental group of these things. But once you group complete, GP stands for group completion, you get interesting higher groups. Very interesting, and even more so that it relates to zeta functions. So it was proved that just like the units and the class group, these are finitely generated abelian groups. Borel could compute their ranks. Again, they have some relatively simple formula in terms of the infinite places. And he could also prove, remarkably, some kind of class number formula, but only up to rational factors. He couldn't pin down those rational factors. There's a regulator involved from higher K groups to some real vector space and some power of pi and some square root of the discriminant. So in the third talk of my series, I will be much more precise about these higher class number formulas, but that's kind of the status 1977, already pretty remarkable. And so then people were wondering, what's this rational factor? Can one also describe this in terms of K groups? Well, first of all, can one compute these K groups? I mean, for the units and the class groups, there's an algorithm for a given number field. The higher K groups are harder to compute, and took a lot of iterations of very deep mathematics to at least arrive at this picture here. So at least the K groups of the integers, one can compute in terms of relatively simple objects. Again, Bernoulli numbers, which are not given in closed form, but they have an easy generating series. So these BKs are classical Bernoulli numbers. And then you have these numbers WK, which are very simple. They're kind of the exponents of these residue class group mod M. I mean, the maximal M for which the group has this exponent K is WK. For example, W2 is 24. The maximal modulus for which Z mod MZ has exponent 2 is 24. And so in terms of these quantities, one can compute K groups except for the indices which are 0 mod 4. So K4 of Z was computed to be 0, but K8, K12, K16, and so on, they're only conjectured to be 0. That's something one can still not prove. So if somebody knows homotopy theory, so K groups are a little bit like homotopy groups of spheres, but they're easier. But they go in this direction, but they're easier than homotopy groups of spheres. Yes.
Question. Could you go back one slide?
Yes.
You may have said it, but I just missed it. What is this R sub 2m minus 1?
Oh, it's a regulator involving a map from the K group to a real vector space.
Ah, okay.
So it's supposed to be analogous to the unit regulator. So we had in the class number formula the unit regulator here, the co-volume of the units, right? I mean, if you've never seen the class number formula, this would be hard, but if you've seen it, it's analogous to the regulator. Does that answer your question? Hello?
Yes, it did.
Okay. So in the mid-70s, this was known, and then this is much later to compute these K groups, as I said, maybe with the work of Wojewodsky around 2000, one could complete this, and then it was written up by Weibel maybe by 2008. And so one can compute these groups, but it's not clear what is the actual integral relationship between the zeta value and these K groups. So far we only have some very coarse relationship up to rational factors, not like the class number formula where everything's nicely integral. So let's go back to zeta of 2, which is pi squared over 6. So you can write it as 2 pi squared over 2 over 48, which is, if you look back at the table, 2 over 48 is just the K2 over the K3. So you might think you have a formula. Okay, so it's something like a certain power of pi, and then you have the cardinality of K2m minus 2 divided by the torsion of K2m minus 1, and a regulator and discriminant, and then maybe up to a power of 2 for m even. Yeah, well, no, actually for any m, because I put in the regulator. For m even, the regulator would be 1, right? Because what happens for m even, if you look here, if you have a totally real field, the R2 is 1, and then Q to the R2 is 0, so you don't have a rank of the K groups. Yeah. Okay, here we are. So such a formula can actually be proven, but it goes through a number of detours. And it's not so clear whether the K groups are the right objects. I mean, certainly one doesn't use the K groups directly to prove this formula. One, first of all, just things prime by prime. So you look at the L primary part of these objects for all primes L. And then you have what's called a Chern class map relating K groups to étale cohomology groups, which are a little bit more concrete. So this ZLM is just a Galois module, which is given by the mth power of the cyclotomic character, the action on roots of unity. So ZLM is a one-dimensional ZL vector space on which the Galois group or the fundamental group of the scheme acts by the mth power of the cyclotomic character. So that's supposed to be relatively concrete and simple. And the Galois cohomology is also relatively concrete because you have theorems like Poitou duality that give you some control over this Galois cohomology. I write it as étale cohomology. So I'm saying Galois cohomology, but I'm writing étale cohomology of the scheme Z1 over L. And it turns out to be the same thing in that case. It's the same thing as the Galois cohomology of the fundamental group of that scheme. And so it turns out these Turing class maps, which I guess were first defined by Soulé, but I think Quillen already had an idea. Soulé wrote it up, and it turns out that they induce isomorphisms between the L completed K group. So because the groups are finitely generated, that's just the tensor with ZL, and this étale cohomology group, except if L is 2 and I is 1. So the K groups are not quite the same as the étale cohomology groups. There can be a difference concerning the 2 primary part. So as an example, K3 of Z maps onto this H1 with Z2 twisted 2 coefficients, but there's a kernel Z mod 2. This H1 is a Z mod 8, and the K3 has order 48, so it has a 16 in it, a factor 16. So there's an extra 2. So I was saying one proves these formulas actually not using K groups, but using this étale cohomology group. So that's Iwasawa theory. So that's another whole different story. So you can relate these étale cohomology groups or Galois cohomology to classical Iwasawa modules. There is what's called the main conjecture, or the theorem of Maser-Wiles in that case, which allows you to relate these to the zeta function. And through a long winding proof, you can prove a formula like this. But it never involves K groups directly. And indeed, K groups are not quite the right objects to describe this L value. They're not right at the 2 primary part. So even though I wrote it like that as an order of a K2 over K3, this factor of 2 shouldn't actually come from the K3. This factor of 2 here, that should actually come from the real place. Okay. So this is just some rough idea that there is an integral story. So there is something that looks analogous to the integral, to the analytic class number formula at all integers. But what's the right way to formulate that? Well, I'm not saying it's the right way, but it's certainly a very intriguing way in the way that's generalizing. And it uses this fundamental line. So I want to introduce this point of view of the fundamental line at this example of the motive Q2, which is the zeta function at S equal 2 for a number field. And if the number field is totally real, then the corresponding K group doesn't have a rank because remember it's K2m minus 1, so it would be K3, but for totally real fields, the K3 is finite. So there's no regulator term coming in. So there's only a power of pi. And the way this works out with this fundamental line is, so the idea is one writes down a certain one-dimensional Q vector space, which I call psi of m, attached to this motive. So the motive is really a piece of the cohomology of spec f twisted twice with a Tate motive. And then it has, as I was saying in the beginning, it has all these cohomology theories attached to it. So it has the Ram, Betty, and so on. And if you work that out for a number field, the de Ram realization is just the number field F itself. And it has only an H0 de Ram. And the M0 here refers to the filtration of your motive. But since we're shifting twice with the Tate twist, the M0 is 0, so we just get M de Ram is F. So that's kind of what's called the tangent space of this motive M in this case. And then you have the Betty realization, but you have to take the plus space. under complex conjugation acting on it. So there's a certain recipe that forms this fundamental line out of the motive and its realizations. And it's that space for totally real number field at s equal 2. And then there's a period isomorphism relating the Ram and Betty quantities. So this period isomorphism allows you, once you tensor this line psi of m with R, that means all the rational spaces that go into it get tensored with R, and then there is an isomorphism between them. Think of a period isomorphism relating Betty and the Ram objects. And so that's kind of the Archimedean part. The period isomorphism allows you to construct a canonical isomorphism of this fundamental line with R. Yeah. I mean, it's just basically bringing things to the other side, right? You have an isomorphism, A tensor R is isomorphic B tensor R, and then you take determinants on both sides, and you have two lines, an isomorphism of two lines, and then you take the inverse of one line to the other side, and what's left on the remaining side is just the constants R. It's canonically the coefficients R. So that's what the period isomorphism gives. And then the way the integral part is described, I mean, this is really done by prime. So for all prime numbers L, you have an isomorphism theta L of this fundamental line tensored with QL, not with QL like in the Archimedean case, but with some other Galois cohomology complex. So you have a canonical isomorphism coming from certain exact sequences and triangles, relating this fundamental line tensored with QL to this compact support étale cohomology with coefficients given by the analytic realizations of your motive. So in general, for this QL2, I would have to plug in ML, the analytic Galois representation attached to this motive. Well, the conjecture just says that you take the zeta value, which is just a real number, zeta f of 2. So it lives in R, and you map it into the, oh, there's an inverse here. No, it should be, okay, maybe I can put my correction again. I like to scribble around, so there shouldn't be an inverse here. Because if theta infinity maps this real number, zeta f of 2, which lives in here, zeta f of 2, it maps it into this other space, and then the rationality conjecture says that it's actually lying in psi m itself, not only in psi m tensor R, so it lies in here. And once it lies in here, you can map it by theta L into this determinant, and then it's supposed to span the natural integral lattice in here, which is the determinant of the integral CL2. So that's a pattern discovered by Fontaine and Perrin-Yu, that you can formulate these L value conjectures prime by prime, and it seems to be true. I mean, there's lots of evidence for it, which I'm going to say more next time. And so just for clarification, this compact support cohomology is defined so that it sits in an exact triangle. So you have the usual étale cohomology R gamma of your scheme, Z1 over L, mapping into the Galois cohomology of the local fields QL and R with these respective coefficients. And then the mapping fiber is the compact support cohomology. It seems to be the right object that describes the R value. Okay, so for example, if M is Q2 and F is Q, the period between the tangent space or the natural lattice in the tangent space, so now I take OF inside F, and the natural lattice in the Betty space, just taking Z coefficients instead of Q coefficients, you get a period of 2 pi, and actually, again, I think there should be a discriminant. So the discriminant term that we had in Borel's formula, or in this formula here, it comes here from the fact that first of all, you have a period isomorphism between F tensor R and the direct sum of all the infinite places of R. And then inside there, you have the Betti with its 2 pi factor. So I think I also have to correct this. So there should also be the square root of the discriminant here. But anyway, it's just to illustrate the general idea how you massage these formulas into something that's related to cohomology. And then you have to so that's kind of the Archimedean period isomorphism between the tangent space and the Betti space. And then you also have a p-adic isomorphism, which is what was discovered by Block-Kato and which started this whole idea of the Tamagawa number conjecture. There's an exponential map from the tangent space tensored with QL, FQL, to this Galois cohomology group locally. Just so we're talking about local concepts now. So the local Galois cohomology of this module QL2 is isomorphic by some exponential map, first constructed by Block-Kato and being at the origin of all these ideas. And this is what's implicit in this isomorphism theta L here. So this involves this triangle, and then you relate the local Galois cohomology that I have here via the exponential map to the F in the tangent space. So that's a key ingredient which was completely new at the time and which is still key for describing L values. So this L-adic exponential map that relates the RAM objects to, L-adically completed Motivic objects, in this case, the Galois cohomology of QL2. And then you look at the corresponding integral structures. So you look at the ring of integers locally, and this is mapped to the corresponding integral Galois cohomology. But there's also an Euler factor, which one has to put in by hand, which comes from the fact that you take cohomology over Z, remove the primes L, right? So implicitly in this story, when one describes the L primary part, you also remove the Euler factor at L, and then you have to put it back in by renormalizing your isomorphisms. So it's not very easy, but it seems to be correct. And so now I'm just writing out the long exact sequence for this exact triangle here. So you have H0RZL2. So these compact support cohomology groups, they have some local contributions from R, which is just, as I'm writing here at the bottom of the screen, it's just a Z mod 2. So this is a local Z mod 2 that's also in the difference between K3 and the Galois cohomology. So remember this this relation between the zeta function and Galois cohomology from the main conjecture involved these groups here. And so if I express this in terms of the compact support groups, I have extra contributions from here and from here, which is sort of my contribution from the tangent space. And then these groups are finite. And so the key ingredients are this one and this one, but then there's other correction terms which together make this compact support cohomology. And they all describe the L value exactly for all primes. Okay, so maybe I'll take a break now and discuss some more of the algebra. So I'm talking about these complexes here, R gamma. So these are complexes constructed using the usual homological algebra formalism of choosing injective resolutions and so on. They're just complexes of ZL modules, but they're very nicely behaved. They're just bounded complexes and with finitely generated cohomology over ZL. So that's the notion of a perfect complex. when you have a perfect complex, you can take its determinant, which is what I was doing here on this slide. So I wanted to explain this concept slightly more generally. So this works over any ring, and again, you can view it as part of K-theory. But now not K-theory on the input, on the geometric objects, but K-theory on the output, on the coefficient, so to speak. So it's a different kind of K-theory. So for any ring, you have the notions of a perfect complex. Again, it's rather simple. So you only look at complexes up to quasi-isomorphism. So there's a zigzag of quasi-isomorphisms between such a nice bounded complex of finitely generated projective modules. So that's a notion we have over any ring, perfect complex. But if the ring is regular and Noetherian, for example, Z or ZL or QL, all these rings we had so far on the level of coefficients, then a complex is perfect if and only if its cohomology is finitely generated in 0 for almost all I. So it's a very simple object, and that's because a finitely generated module over a regular ring has a finite projective resolution. So you can view it itself as a perfect complex. And then for a perfect complex, you have two invariants. Let's say R is commutative, because in general, you don't have a rank function. But for commutative rings, you have a rank function. So it's just the usual rank of a projective module. So a projective module is locally free. And so the rank is well defined locally. And then globally, it's a locally constant function on the spectrum of the ring. So it could be different on different connected components, but it's just an integer. And then you have the determinant, which is the highest exterior power of each pi, and you tensor them up with alternating signs, where the inverse is just the dual rank 1 module. So you get a certain invertible R module that's functorial in the perfect complex. So the heart of the theory is the statement that there's a well-defined determinant functor from the derived category of perfect complexes to invertible modules. So, of course, on the level of objects, if you have such a concrete complex of finitely generated projectives, you write down the determinant, but you have to show it only depends on the quasi-isomorphism class. And then you have a nice calculus of these determinants. So for any short exact sequence, or more generally exact triangle, I mean, if you use the language of stable infinity categories, it's much nicer to formulate. If you use triangulated categories, it's a headache to formulate, and it's not quite correct that for any exact triangle you have this isomorphism. So that's why I'm saying short exact sequence. You get an isomorphism of the middle with the determinants of the outer terms. If you have an acyclic complex, you get a canonical isomorphism of the determinant with base ring. So in other words, you get a canonical section of the, if you have an invertible module, it need not be free, it need not have a basis. But once you can produce a canonical section, you identify it with a base ring R. It's free of rank 1. Any quasi-isomorphism induces isomorphism of determinants, and then if R is regular Noetherian, the determinant is isomorphic to the determinant of the cohomology, which are themselves perfect complexes. So there's a slight correction needed to what I was saying. Namely, these isomorphisms associated to an exact sequence, they depend on the ordering. So let's say the C2 in the middle is actually the direct sum of C1 and C3. And I don't specify which is the subcomplex and which is the quotient. I could choose either. So then there's an ambiguity. So I get a sign ambiguity. So just as an example, if you have a free rank 1 R module and you take V plus V, which is a perfect finitely generated projective module, and then you flip the two factors, they also get flipped on the determinant. And the determinant of a rank 1 module is canonically V, so you get a flip map on V tensor V. But somehow this is not commutative because on the determinant of this V plus V, I have to take the wedge product. So if I flip the two basis vectors, I pick up a minus sign. Whereas on the usual tensor product, I don't have that with the standard conventions. So, so if I don't specify an ordering in a direct sum, I would get an ambiguity of these isomorphisms, which would mess up my special value conjectures. And the way out of this is to actually retain the rank information. So we don't take determinants as taking values in invertible modules. We let them take values in graded invertible modules or line bundles, which are pairs of a line bundle and such a function, an integer valued function. And so if you take the determinant, you just retain the rank information. So it's a capital det is my usual det, comma the rank information. And my target category of graded line bundles now has a modified commutativity constraint. If I switch two sections, I pick up a sign depending on the grading. And then once I make my target this refined category, I don't have to worry about choosing orderings or something. All isomorphisms are now canonical again if I retain this rank information. Okay. So let's see how this determinant of perfect complexes works out in the case that interests us. I was taking determinants over ZL before, right? So let's say I have a finite module over ZL that's a perfect complex because it has a two-step free resolution by ZL modules. And but if I tensor it with QL, it becomes acyclic, it becomes 0. So its determinant rationally is canonically QL. And then if you work out this formalism, the determinant of the integral complex M inside the rational complex is just given by the order of the group, but with an inverse. So this determinant formalism picks up orders of finite cohomology groups sitting inside rational vector spaces. Okay, so ZL is a little bit easy. You could take things, for example, you could take a group ring. For example, if I have a number field spec F like before and the Galois group acts on it, it will act on all the realizations, it would act everywhere. So everywhere I have set ZLG modules instead of just ZL modules. And as I will be explaining next time, this whole formalism will go through with such refined coefficients. So for example, I could have some finite free ZL algebra, finitely generated projective R module with a Galois action, as I was writing here. And then it turns out that this compact support cohomology and the local cohomology are still perfect complexes, whereas the usual cohomology is not in general. So that's another advantage of this compact support cohomology. It's always a perfect complex. I can always take determinants, even if I have some non-regular coefficients like a group ring, where not every finite module is perfect. But still I have a perfect complex, and this will occur in the special value conjectures. Okay, so that's just some piece of algebra pertaining to the output, so to speak, how I transform my cohomology theories into something related to the zeta function. I'll take determinants and see what it does to these various isomorphisms like regulator and period isomorphisms. Okay, so yeah, so maybe I can be brief here, but how does the class number formula actually look like from this strange point of view of the fundamental line and the Tamagawa number conjecture? It does translate, so the motive is just the Tate motive 1 over the number field. It has a Betti realization, which is just the sum over all complex embeddings of 2 pi I, the basic free space spanned by the complex embeddings multiplied with 2 pi I. But then I have the I have the Galois group of the real numbers acting on it. So it acts on C via the second argument in this Hom F, C space, but it also acts on 2 pi I. So it has this diagonal action. And then there is a certain recipe which produces a fundamental line from this motive involving, again, a tangent space, which is F in this case, some Betti plus space, which is just seeing the complex places, because it's actually a minus I space because of this action on 2 pi I, which sends I to minus I. So the plus space is actually 2 pi I times the difference of these two embeddings. And then I have other ingredients in the fundamental line which didn't occur in my previous example of Q2 because the K groups had trivial rank. But then there's other ingredients which are things like algebraic K groups, or rather Adams eigenspaces of algebraic K groups. They coincided again by accident with full K groups because spec F is 0-dimensional. It so has such a small dimension. But in general, there's what's called Motivic homology spaces, which I call H1FM and H0FM, which are made out of algebraic K groups or higher Chow groups, as you like. They're isomorphic rationally. And they're also part of the fundamental line. And they're involved in regulator terms, right? So periods just involve the Ram and Betti and the period isomorphism. And then I have things like Motivic homology or K groups, which are related to the other groups by a regulator map. So I'm specializing this general recipe to the class number formula to Q1. Again, the Motivic homology group H1FM would just be the units, but now rational. So that's my first ingredient in this fundamental line. Then I have a dual motive M star 1. So the dual of Q1 is Q. And of this dual motive, I have some H0, which is a certain Chow group. You can view it as a group spanned by the cyclic class of a point in the Chow 0 of spec F. So that's just one copy of Q, but it has a canonical basis. And then I have a tangent space F and I have Betti space. And they're related. Once I tensor these Q vector spaces with R, there are maps between them, regulator and period maps. So that's the idea. So there's a map alpha M sending the Betti plus space tensored with R to the tangent space tensored with R, which is just, if I tensor the number field F with R, I just get the sum over the complex places. Sorry, the infinite places. And then this Betti plus space just consists of the minus part for the complex places. So that means I end up with one copy of R in the co-kernel. So my co-kernel here is just the sum over the infinite places of the real numbers. That's my co-kernel of this map alpha M. And the regulator lands in this co-kernel, which you can also identify as a Deligne cohomology group. But for now, it's just a recipe made out of all these realizations of the motive. And I have a regulator map, which is for the class number formula, it's just a log map, the log absolute value map on the units. And I have one such map for each infinite place. So I land in this direct sum of copies of R over the infinite places. And again, my regulator period maps give me an isomorphism theta infinity between this fundamental line tensor R and R. So that just means I take a basis eta 1 up to eta something of the units, Z basis of the units modulo torsion. I take a Z basis of the tangents, the integral tangent space OF, and then I have, as I was saying before, this H0F has a canonical basis, so that's what I call 1 star here. And the Betti thing has a canonical Z basis given by the embeddings, and then I look what this does under the period and regulator isomorphisms, and I get 2 pi to the R2 R divided by the discriminant. So if I take this section here, the wedge product of the etas and the omegas, etc., and I see what it does on the left-hand side of my theta infinity, I get this number, 2 pi to the R2 R over square root of t, which is the transcendental part in the class number formula. And then to get the other terms, I have to do my game prime by prime according to this recipe. And I'm almost out of time, so I will be quick with this stuff. So again, I have my compact support cohomology. I relate it to the terms in the fundamental line by a certain exact triangle, mapping compact support to what's called F cohomology, which is some version of the cohomology of the ring of integers, but made out of just objects pertaining to the generic fiber F. And then I have the local fields, F tensor QL, F tensor R. And using this triangle, I will end up with an isomorphism of the fundamental line tensor QL with a compact support cohomology. And again, locally, I will have the exponential map. This time it's just the usual exponential map, right? It's the exponential map from the additive group to the multiplicative group. That's for what happens as S equal 1. No strange Block-Kato exponential, which was much more sophisticated construction. Because I have an algebraic group at S equal 1. My Motivic cohomology groups basically coincide with the algebraic group GM. My exponential map is involved in this isomorphisms. I have my Euler factor comes out as a local volume, and then the class number formula, which is what you have to believe me now, is really equivalent to the last statement on this slide, saying that if I take my leading coefficient of the L value, which is the residue, and I map it into this compact support cohomology, I just get the corresponding integral compact support cohomology. And I see there's another typo. And this should be the ZL cohomology here. Okay, so this is the pattern. I mean, it's very counterintuitive, and it's a miracle that it works, but it involves this determinant formalism of perfect complexes. So you can view the class number formula like this. It's not clear why it's called Tamagawa number conjecture from this point of view. I don't have time to explain this, but Tamagawa numbers is sort of something associated to algebraic groups, but that only works for S equal 1. For higher integers, you have Motivic cohomology groups. You don't have algebraic groups. But Block-Kato treated these Motivic cohomology groups as if they were algebraic groups. They have a tangent space, they have an exponential map, etc. Okay, so now, so I'm saying Block-Kato had the initial idea of the Tamagawa number conjecture. It looked very different. What I was explaining here with the fundamental line is due to Fontaine and Perriou. And what are the advantages of this? Well, it generalizes to negative integers. So far we only discussed the region where the L function converges or almost converges at S equal 1. But as you might know, it can be continued. And there's also actually a much simpler formula for the negative integers. If you have the class number formula in your mind, it's actually much simpler at S equals 0. And this whole recipe of forming a fundamental line and so on also works for negative integers. So I found that the most amazing part. Then, of course, there's a question, is it compatible with the functional equation and so on? It generalizes to all Hasse-Weil L functions of motives, which is the class of L functions I was referring to at the beginning, at any integer argument, not only positive ones or of appropriate weight. And you can throw in coefficients. So you can throw in extra symmetries of your objects, like a Galois action in a number field, or an endomorphism action on an abelian variety. And you can make all these determinants over this acting algebra A that expresses extra symmetries of your motive. So this is certainly a very general formalism that seems to be correct in all these incarnations that I was mentioning. Okay, just to finish, let me give a little bit of a timeline for this. So again, as probably the first special value formula was Leibniz formula, or Gregory's formula, pi over 4. Euler discovered his formula. Then the class number formula was first discovered by Dirichlet for quadratic fields in a different language, of quadratic forms probably. Then Kummer for cyclotomic fields. Riemann looked at the zeta function complex arguments, gave the analytic continuation. of course, we gave the Riemann hypothesis, but we're not concerned with the zeros, we're concerned with the values. So Dedekind 1896 proved the class number formula as I was discussing, but at that point, the general analytic continuation and functional equation wasn't known. That was done by Hecke, 1917. And then things moved into global fields of characteristic P, which I haven't said anything about, but it's covered by the point of view of arithmetic schemes that I will talk about later. So these are analogous to number fields, and they also have zeta functions, and zeta functions are much simpler. They're basically rational functions. And has already proved the Riemann hypothesis in the genus 1 case, and then they generalized this to arbitrary dimension. Ono gave his formula for Tamagawa numbers of Torah, and then Tamagawa numbers of algebraic groups were much studied by Weil and so on in the early 60s, and inspired by that, Bertrand and Dyer gave their BSD conjecture for elliptic curves. So meanwhile, over finite fields, Grothendieck had this general beautiful theory in terms of analytic cohomology. So of course, over number fields, which was what I was discussing today, you only describe the values in terms of analytic cohomology, not the functions, because you have all residue characteristics on your arithmetic scheme. Okay, Tate, BSD in general. The general definition of Motivic L functions, which I will give next time, given by Serre, and then a key input algebraic K theory, defined by Quillen, early 70s. Borel's work I already mentioned. First results on BSD, Coates Wiles in 76. And then Bloch looked at elliptic curves, not at s equal 1, which is the BSD point, but at s equal 2, and related that to K2. And so these conjectures were slowly building up from concrete cases. And Deligne made a rationality conjecture in the critical case, which is what I was discussing in the case of Q2, where you don't have a regulator, you only have period terms. That's called a critical motive. And then in terms of proofs, results kept coming with Grossagier's formula, the Iwasawa main conjecture, as I was mentioning, allowed to prove special value conjectures for cyclotomic fields. And then Beilinson removed the construction to critical motives. So we had a rationality conjecture generalizing Deligne's in general. And then, of course, the question was, how do we get an integrality conjecture? That was done by Block-Kato, 88. But from the point of view of Tamagawa numbers, and then proofs came also in the mid-80s using Euler systems. So other people in this conference will say much more about this. So you could actually prove instances of this picture. 1991, Fontaine-Perriot introduced this fundamental line point of view, which is what I'm going to discuss in these talks. And then, motivated by Gauer model theory with David Burns, I actually made a conjecture even over the group ring, where the coefficients are not regular, but one still has some subtle special value conjectures relating, for example, Artin-L functions for all characters of a given Gauer extension. And then again, proofs kept coming for special cases. TNC for Dirichlet L functions is completely known, and also the equivariant one, Franz Kreiter. The general picture was probably what's the most general conjecture on these special values for arbitrary analytic families, not just analytic realizations of a motive, but for an arbitrary analytic family. You can view this as the most general Iwasawa main conjecture made by Fukaya Kato. And then again, proofs kept coming by Skinner, Kato, elliptic curves over Q. So now my historical expertise stops. There's much more work, of course, done after the early 2000s, where this basically stops here. And you will hear more about that in other talks. Okay, I'm already running over time. Maybe it's time for questions.
All right, so that's all. Anyone else? If not, let's thank Matthias again.
Okay, thank you.